Hello, learners. This is Katie.
I'm Vinny, and this is Learn Real Good.
Oh, man, I am so pumped.
I'm
Every time we
excited.
record, I am so jazzed.
I like learning. That's the whole theme of this show, and we're going to learn some more today. So let's get to it.
Yes, well, for our new listeners, because every week we have new droves of listeners out there who might not know what the show is all about. So let's remind them how this show works. We are going to chat a bit.
Yeah, share some
Catch
facts.
up, because we haven't seen each other in a while. We're going to share...
We live together.
Yeah, and it's a pandemic, so we see each other 24/7. We will share a fact that we each have brought to the table that has not been shared ahead of time, which is really exciting.
That's exciting.
And then we get to the best part, which is our amazing guests. And we will be interviewing them about their research and their life as a grad student.
Mm-hmm.
And that'll be it. That's enough learning, though. I feel.
We don't want to overstimulate our audience.
Yes. I mean, an hour a week is what I think is the recommended dose of learning.
45 minutes tops. The extra 15 minutes is just overkill.
Very controversial considering how education works traditionally.
Yeah, a full day.
A full day.
Yeah.
Over. Too much.
Too much. Just 45 minutes of school. That's my new recommendation.
Do you remember how exhausting school was as a kid?
Yeah, it finished at like 2:45, and I was like, oh, who can do anything for this long?
I remember, actually, I have a very vivid memory of my older brother coming home from his first full day of school. My older brother is 3 years older, and he came home and he was just exhausted. And I was like, let's play. And he just like leaned over on the couch and just like passed out. I was like, oof, tough one.
It's hard. Well, I mean, you've never had anything that hard before, so it's literally the hardest thing you've done up until that point.
It's true. That's a wake-up call right there.
Sure.
First day of school after just years of tomfoolery.
Yeah. And then you get like summer vacation, and then you're the real world.
Well, or you can stay in academia forever and always have summer vacation. Except for when I did field work, I've always had the summers off.
It's
and
not
I
bad.
don't know how people do without.
Now, Katie, do you want to hear my fun science
Oh my
fact?
gosh. I'm ready.
Are you ready?
Bring it.
All right. So have you heard of forest fires?
I think I have.
Yeah, these are fires
I've
that
heard
happen in the
rumors.
forest.
Oh, okay.
It's pretty good. They're well named, very clear. There's a fire in the forest. Now, have you heard of zombie fires?
Ooh.
And I'm hoping you haven't, because that's the whole point of this.
I've never heard that term before,
Okay.
but I bet I know what it is.
Well, I want to hear what you think it is.
Okay, yeah, that's fun.
Yeah.
So I mean, given what zombies are,
Right.
they're undead and they sort of come back to life. I
Yes.
assume it's like the flames have gone out, but there's so much heat that they can reignite.
Okay, you're close.
Oh, damn.
So these are fires. So people started noticing like satellites supervising forest fires, kind of tracking how much of the wilderness is burning up every year. And people started noticing that new fires were emerging very near to the site of fires from the previous year. And so like, what's happening there? Is this a coincidence, or is there something happening? And what they've noticed is that up north in the boreal forests, forest fires would set the ground on fire, and then as the winter came in, the snow would cover it up, but the ground would still, like, it would still have vents and get fed, and the ground would stay on fire, and then when the snow retreated, it would reignite and resume.
No.
Yes.
So snow, even being covered in snow wasn't enough to lower the temperature.
Correct.
Wow.
It is, and it goes down into the earth. Like, it goes like tens of meters down into the ground, that this fire just smolders and the heat is there and it survives. And then when the snow retreats, it comes back. Now, this was not a well-known, from what I've read, this was not a well-known phenomenon, because the winters used to be longer than they are. And so now they're noticing that this is becoming more and more common. And so this is a real phenomenon that, as climate change progresses, is going to affect the boreal forests.
Wow. Yeah, you never think of ground. Ground always seems like safe from
Sure.
fire, right? I guess just because it's so saturated with moisture, it seems like...
Right. But there's peat and bogs
Yeah.
and all of that decaying fuel that's just sitting there.
Wow. And the only thing that's kept it from happening before is that the winters were too long.
Mm-hmm.
That's nuts. See, these are these unpredictable things. Like, how could you have thought of that?
No one thought of this.
No one thought of that. Wait.
I certainly didn't.
Well, maybe our guest did. We'll see.
Yeah. All right, Katie.
Oh my gosh. Okay. So this is about worms.
I'm excited already.
Are you ready?
Who doesn't love worms?
I'm just going to disclose the story one noun at a time.
Worms.
Worms.
Picture this.
Yes, worms with heads and then no heads. So there's flatworms, okay, who have eyes. They're really cute. Have you ever seen like a flatworm? Anyway,
Did you say they
I'll
were
show you a
cute?
I think everything's cute in
Okay.
its own right. I mean, people used to slag off baby birds, saying they're ugly.
Did they?
If you've ever seen a newborn baby
Sure,
bird,
yeah.
it's a little hard to. Only a mother could love that. They've got these little pink nubbins without the feathers.
Okay.
I always thought they were adorable. Anyway, I think flatworms are adorable. All living things
Sure.
are sweet and adorable. Anyway, they have big eyes.
Okay.
And like anything else with eyes,
Uh-huh.
they use their eyes to...
See.
That's it. Okay, to sense primarily light, right? They're not doing some high-tech 3D
Right.
vision. They're just looking for...
They have two eyes?
Yeah.
So they must have some.
I mean, I don't know what high-tech 3D vision I was thinking of, but I mean, like, they're not doing...
Did you pick like some Mission Impossible 3D scan of a
Yeah.
room? Yeah.
Yeah, like the Terminator. No, like, what are those mantis shrimps? They have, like, all these cones and stuff. You see all
Sure.
these colors. Anyway, they got eyes, okay? And they primarily use their eyes to see light. And we'll get to why that is important for them to do. But here, the interesting thing, and this comes from Nature News in May, scientists recently noticed that if you behead these worms,
Uh-huh.
they can still see.
What?
Right. They can still move away from light. So that's normally what they're doing, is they move away from light with their eyes, with their heads intact, or without their heads. They will die eventually, but for the brief time they're alive without their heads, they can still sense light. So what they found was that they have light sensing cells all over their body, and that this isn't an inborn thing. So baby worms can only see light with their eyes. The rest of their body can't. So it's something that develops along the way towards adulthood or during adulthood. And what I want to see if you can guess, since I had a guess during your fact,
Uh-huh.
is why what would be the value, the evolutionary value of being able to sense light without your eyes?
I guess if a bird bites your head off, you still want to go back underground and somehow try to survive?
You're going to die. So it's not to do with beheading, even though that's how it was discovered. But why would be the value of other parts of your body
being
sensing light
sensitive.
without your eyes being used?
Suntanning.
They move away from light.
Anti-suntanning.
So
Avoiding sun. They sunburn easily. They're very fair.
they want a tan. They have a desire to tan, but a very
they
limited
can't.
amount.
Yeah. It's a tragic tale.
No, sadly, we're a little off the mark. It is because they're nocturnal. And so they want to be able to move away from light even if they're sleeping. So during the daytime, when they've got their little eyes closed and they're sleeping, the rest of their body can still sense if there's light and move away from it, even though their eyes are closed.
This is a podcast, so no one could see that you made a very cute little sleeping worm gesture with your eyes closed.
I've been working on my sleeping worm. I appreciate that you see
Yeah.
it. I'm sorry viewers are missing out
You are missing
on my worm impressions.
Yeah, if you ever meet Katie in person, you can ask her to do her sleeping worm impression.
Would love to.
It's worth it.
I guarantee that. I can't guarantee it'll be satisfying, but that's I can guarantee I'll try.
Oh, that's fascinating.
Yeah, I remember.
So sleeping.
Yeah.
I mean, I already didn't know that worm. You could have just said, "Hey, did you know worms sleep?" And I'd have my mind blown already. You one-upped it.
I had my mind blown by worms at a very young age. I've never shared this with you. You may be shocked to know this. I have a bit of
also may not be shocked.
I have a bit of history of experimenting with insects and other invertebrates.
Uh-huh.
Okay, I used to put ants. This
is pre-ethics boards.
Yeah, this is 4 or 5-year-old Katie. I would take like old margarine containers, margarine containers. My mother would always save every plastic container she had. And I would fill with water, and then I would create like an obstacle course of grass, like floating on top of the water to like make a path from one end of the container to the other. And I would put ants to see if they could make it.
Mm-hmm.
And if they fell into the water, I would try to save them. Sometimes worked, sometimes didn't. I mean, I guess it's animal torture, but that wasn't how I saw it.
No, you were 4.
Anyway, another experiment was I cut up an earthworm
Okay, I'm listening.
And then the little parts of it scurried away, and it blew my mind.
Right. Wow.
Yeah. I was like, how did that happen?
How'd they know where you were? Now we know.
It was right to run away.
I mean, yes.
But yeah, it's tragic, eh?
That's amazing.
Yeah. Sorry, Earthworm. This episode is dedicated to the Earthworm whose life was lost.
Yeah.
In the early development
Shout
of my
out
scientific
Earthworm.
career. All right, enough goofing around. Are you ready to get to the
Yes.
main bit? Okay, so I have the pleasure of introducing this week's guest, Amanda Kotila, who's a master's student in the Earth and Atmospheric Sciences Department at the University of Alberta. Her research focus is glacier melt and evolution modeling in the Canadian Rocky Mountains. She has a bachelor's in geosciences from the University of Montana, where she focused on hydrology and climate. Amanda loves all things cold climate, as well as reading, hiking, dancing, and cross-country skiing. Her dream is to study glaciers on the ice in Antarctica.
Wow.
Please join me in welcoming Amanda. Amanda, get in
Hey.
here.
Hello, thank you so much for having me.
Oh, it's a delight to have you. Thank you
Yeah.
for fitting us into your day and not fleeing when you heard of my past, my dark past.
I'm excited to be here on the special In Memoriam Worms episode.
That's right. Yeah.
Yeah, you didn't know that ahead of
We
time.
have a whole slideshow set to somber music at the end.
Yeah, in the
Nothing
arms
com-
of an angel worms.
That's right.
It's beautiful.
Yeah.
So, Amanda, you work with glaciers. Let's start with what brought you to glaciers? What made you interested in pursuing that line of research?
Oh, wow. I think it started, so I grew up in Montana mainly, but when I was small, we lived not too far from Seattle. And so there's the scenic skyline, and you could see Mount Rainier from our house. It's that majestic snow-covered mountain year round. It was gorgeous. I loved playing in the snow. And I got fascinated with Antarctica at a young age, kind of the age of exploration of Antarctica. Some of it was the biology there, the penguins and stuff. You read Mr. Popper's Penguins, and you read about, Cook and Amundsen and Scott going down there. And so I just thought they were a fascinating thing that happens on parts of the globe. And so after doing a lot of studying in physics and realizing what an interesting physical systems glaciers were, I decided to continue to pursue that.
Very cool.
That's very cool. And I have to say, I didn't even pick my winter fact based on your field. Only after I was like, yeah. It was a total coincidence. So
Lovely.
Sure it was. Pandering, Vinny.
all right. Well, you like me more now, Rilla, right?
Those are cold weather worms, by the way.
Uh-huh.
So I guess for people who aren't aware, what is a glacier? Do you want to explain what a glacier is and what's their significance geologically speaking?
Okay, yes. Two different questions. Let's start. So a glacier is a basically gigantic mass of ice with other debris and snow thrown on there for good measure. So they were formed during ice ages or extreme periods in the Earth history where it was cold, and allowed for glaciers to form from the snow. And perhaps we'll talk about this a bit later, but glacial ice isn't like letting ice freeze on the surface of the lake or in your freezer. It actually happens very slowly over time through metamorphism from snow into ice. And so if you cored a glacier, you would see the whole process happening from the snow at the top through the fern layer, which is in between snow and ice, and then the compacted glacial ice at the bottom. So yeah, it's ice. And then it's so heavy, it's such a large mass because it happens at kind of almost the mountainous scale to the whole regional continental scale like Antarctica. It gets debris trapped in it as it flows under its own weight. Glaciers actually flow, and they pick up ice, and they pick up boulders and other stuff. So yeah, there's other stuff mixed in there, but it's mostly ice. And they are significant because, they were formed during parts of the Earth's history. They are what we consider in hydrology to be fossil water. So it's ancient water that is stored and is slowly being released during its natural melt cycles. It's a store of fresh water, which is very rare on the surface of the earth, and that it's not lost seasonally as well, like seasonal snow is lost.
Hmm.
And it's also considered a natural reservoir. So they happen at either high latitudes or high altitudes. So if you think of the Himalaya, the people downstream use that fresh water. So not only is it storing this ancient fresh water, but as it releases it, there's a natural cycle of flowing from high elevation to low elevation, and the whole ecosystem and downstream anthropogenic users can use it and not have to move it around like lake and river water.
Now, how does a glacier move? I know they move. How does that work?
Little trucks,
Yeah,
big trucks.
well, it's actually the glacial worms. They
Yeah.
go under the glacier.
Makes sense now.
Nice.
Yeah. This is where we get into the quite complicated physics of
Uh-huh.
glacier dynamics, and it's somewhat understood. You can read papers, there are equations, but us glaciologists know that
Right.
there's other stuff. The bandwidth of air, the fudge factors, it's heavy fudge, it's dark chocolate fudge. But mostly it's due to the, like I said, kind of the mass of itself. So the more mass it has and the way it's kind of concentrated along the glacier will then affect how gravity affects it.
Mhm.
And it kind of flows under a continuum mechanics. So if you think about making a pancake and you put that mass in the center of your pan and it slowly flows out in all directions, that's kind of how glaciers move, or they would
Ah.
move. That's how ice caps move because they're less inhibited. But mountainous glaciers, they're stuck on your topology. They have friction against whatever surface they're on, and so that slows them down. But
So
yeah, it's
less pancake, more waffle.
yeah, it's very dense, icy pancake things happening. So yeah, it's got that smooth kind of action that it flows against, but also like it's ice. It's a type of mineral. It gets caught on rocks, and so you have like slip faulting happening at times. You've
Hmm.
got it shearing and tearing against things. So there's a lot of things happening, and that's not only at the margins, but also within the glacier itself. Like you think of it, it will have fissures and cracks as it parts of it are under different tension than other parts. So yeah, there's a lot of physics happening at the micro scale and the macro scale of the glacier.
Whoa, very cool. I'm fascinated by like how to think of ice, because I guess our everyday experience with ice is as this like on a small scale, very solid. We don't have that experience with it as like a very, very like, because glaciers are extremely large generally. And so we're not used to a solid moving on that kind of scale. It's just not something we have an experience with. And so it's really hard to be intuitive about it. Thinking of it having ice flows and glaciers moving down valleys. It's not something like I could, yeah, but when you make it like pancake batter, then I'm like, I get it.
There's a seasonality to it as well. So yeah, you can watch, there's awesome footage, especially a lot recently from Greenland, of a time lapse, and you can actually see the river of ice them come down. So not only is there kind of the constant flow under gravity, but during the melt season, not only do they melt at the surface, but due to the friction, they melt at the base. And so there's what we call basal slip, and it gets lubricated basically by whatever meltwater happens. And so they speed up in the summer and slide along, kind of slip and slide down whatever surface they're on. And so there's seasons of that as well. And that can happen quite quickly, especially as they meet the ocean. And this is happening quite often in Antarctica as well as Greenland and Alaska, where depending on the tides and the season, ocean water can get under the glacier as well and kind of bring it into the ocean faster. And they've noticed this not only with trying to go down under the glacier and see kind of the water melting from underneath the glacier, but with satellite imagery, you can see kind of the ice shelf of an oceanic glacier quickly project and then retreat, or the seasonality again of it moving constantly, constant motion in the glacier world, slowly and quickly at all time scales.
I love it. And so can you tell us a little bit more about your research then? What is it that you're looking at?
Okay, so There's many different glaciers across the world, not only classified by their size, but their type. The continental ice sheets are Antarctica and then Greenland. And then you've got ice caps or ice fields, which are smaller but kind of large conglomerates of glacier. If you stood on it, you'd feel like glacier was around you in every direction. And then you've got your small scale glaciers that tend to be mountainous, and those can be classified as either coastal or continental. So I'm here in Alberta looking at the Canadian Rocky Mountains, and I'm working with continental mountainous glaciers. So most of them are quite small, under a square kilometer, and yeah, kind of interspersed at high altitudes along the Rockies.
Do you have like a pet glacier, like a favorite glacier that you're studying, or are all your glacier children equal in your eyes?
They are all equal in my eyes. So it's interesting. They are all numbered, but they're not all named.
Oh.
And so my heart goes out to like the no-name small glaciers, where I'm like, scientists gave you a number, but they don't give you a name. So
And you can't just name them after yourself?
I should just have my own glacier inventory.
Yes.
That should be my publication, my master's thesis. Forget all the stats. I just spent this whole time naming all these glaciers.
Yeah. Here's an index of all the glaciers that need names.
But there's some very cool. We have a small ice field here in Alberta that you can see when you visit, which feeds both huge watersheds here in Alberta, but also on the BC side. So people probably will know Athabasca Glacier. They can come visit it.
I've been there twice.
More than I have.
Oh no.
I'll get there one day, but yeah, people are like, oh man, you're studying glaciers. I'm like, I model them. People have already visited them for me. I should go see them, but it's not inherent in my work at this point to actually be out on the glacier.
Oh, that's so sad. You're just too busy working.
Yeah. So yeah, in my free time, I'll visit them.
Yeah.
So I've heard of glacial retreat.
Yeah.
What is that, like the summer movement you were talking about, or is that something, a different type of movement?
Okay, so I think probably in the context that you would hear glacier retreat is loss of mass from the glacier. You actually see it shrinking, and whatever its previous boundary was, it's behind that now. And so until we could really see glaciers and have a lot of statistics on them, we have a few here and there where at the early part of the century, maybe there were photographs taken of them. But since satellites is when really glaciology kind of came into its own. And so you can think of a glacier in like the most simplistic physics that we do as a mass system that it gains mass in the wintertime when snows fall on it, and then it melts in the summer and loses mass. And when it gains mass and loses an equal amount of mass, it's in equilibrium. And so people believe that until recently, we have seen most glaciers in equilibrium. Like people in the Alps are used to seeing the ones in the Alps. Same here in the Rockies. Early photos of Antarctica, they were that way for a while. And then now that we can observe them more with satellites and then kind of see increased warming trends and increased retreat, that they are no longer in equilibrium. So they are retreating because they are losing more mass than they gain. And so they're actually, shrinking down. There are a few glaciers that are advancing or gaining mass, but that's very, very rare. The only one I can think of off the top of my head is actually in Mount St. Helens. Like after it blew off, there's a portion of it that's sheltered from the rim of the crater. And so that one is gaining mass. But most glaciers in the glacier inventory are.
Is it only gaining because it blew it out and it's just sort of replacing what was lost?
No, it's actually not even replacing what was lost, but even adding to its mass. And it's just because the whole topography around it changed, that it's shaded. It kind of catches more snow. And so, it's actually turning more snow into ice there.
Nice work, Glacier.
Yeah. You're trying to make up for everywhere else in the world. So glacier retreat is the loss of mass from glaciers that we are observing.
And we will get back to that conundrum of climate
Yeah.
change.
I have a question of something you said earlier that kind of caught my interest because I've never heard of this before, which is the fern layer.
Oh, yeah.
Yes.
And so, can you tell me more? So, like, snow falls on top of the glacier. It's snow. At the bottom, it's ice. Now, what is the fern layer?
Fern is fun. So in between is the fern, and there's actually kind of several different layers within the fern itself. So yeah, between where the snow and the ice is the fern layer, also known as the percolation zone. So if you
That's
think
what
of
I normally call it.
yeah. So if you think of snow when it first falls, it's light, it's fluffy, it's mostly air in between a few ice crystals. And then think about your own experience with snow as winter progresses. It kind of changes. You might get hoarfrost on the top, it compacts, it's more grainy. That's the ice crystals itself degrading from like a picture perfect snowflake to it starts to round out either through small scale melt on each individual flake. Actually, there is wicking of molecules from the outside of snowflakes in between because there's actually you can't see this on a podcast, but if you think of the tips of the points of a snowflake, those are at a slightly higher vapor pressure. And so they tend to move towards the center of the flake because there's a small pressure gradient there. So through melt, through pressure gradients, they start to round, and then through friction amongst themselves as well. So over the winter, the snow starts to round itself out. As that's happening, another process called sintering also occurs, where whatever moisture is on the outside, like if it is a warm day and there is some melt, they also start to join together a little bit. Like there's melting and freezing happening. And so it's no longer a fluffy pile of snow, but more of a snow bank or like a frosty patch. And there's still quite a lot of air. It's just now connected by pores, and it's less connected because there's these centers of ice connecting them in between. So that's kind of your first season of snow. And then as that gets compacted in later seasons by the weight of new masses of snow on top of it, it's almost like sedimentary rock formation where the metamorphosis happens. It's now under greater pressure. So the sintering continues to occur. It gets more and more compacted. It gets more dense than freshly fallen snow until eventually it gets so compacted that there's no more pore space for air or for water, and it freezes into the solid glacial ice. Yeah, so the fern is kind of everything between fresh snow and ice. It can be tens of meters up to a kilometer, depending on what part of the glacier and where on the glacier you are. Like if you are in what we call the accumulation zone, usually the highest altitude where there's more, that can happen. And then the ablation zone at the lower elevations where it tends to melt more and just be bare ice on the edges of the glacier. There's very little fern usually. But yeah, it takes many years for that to happen. And then there's a lot of things that happen in between as well. So within the fern, so it's also called the percolation zone because until it's glacial ice, air and water can get in there. So in the melt summer, when the snow on the surface, if it's in an area that in the summer regions it'll melt, it can seep down like soil. It'll percolate into the fern itself, depending on how well connected the fern is, how porous it is. It can get down in there. And that can actually cause more or less freezing to happen if you think about latent heat. So it actually brings heat because it's warm water, and it can cause the fern to melt, and it'll cause different dynamics to happen. And there's kind of a new study in glaciology looking at the percolation zone, because depending on like if it's warm during the day and it percolates, but maybe it's not well connected, or it melts an area and the water kind of pools in the percolation zone, but at night it gets cold and it freezes, you then have a sheet of ice in the fern, and that's called a lens. And that can happen. That's just a sporadic kind of thing that can end up rapidly or randomly in the fern. And then those are trapped in there, and those get metamorphosed as well. But we're finding that if you have more lenses, that impedes percolation, because then there's sheets of ice that it's trying to get through. And so whatever melt you have runs along the ice and goes. And so it really messes with your dynamics.
Whoa. So, Amanda, I got a wild question for you. I feel like every episode I have like a
Go for
zany
it.
question.
Bring it.
Is ice just ice? Or if I were to give you an equal-sized cube of ice made in my freezer from the fern layer or from the base of a glacier, could you look at it either with the naked eye or a microscope and be able to tell whether it was freezer ice or glacier ice? Like, is the structure different, or once it becomes ice, it's just ice? It doesn't matter how it was formed.
Oh, that's a very good question. I'm going to do the very scientific "it depends" answer.
That's a great answer.
That's great.
I think it's both. So on the one hand, ice is ice. We know water only freezes one way. The literal molecules of themselves are going to join to form a solid. But I think, I'm not an ice expert per se, but I believe that if you handed me cubes from the freezer, from the fern, and from the base glacial ice, I probably could tell with the naked eye that they were different. Someone who is more of an expert, like I know someone who works in our ice core lab who like looks at ice under a microscope, they would definitely know. But my first thought would be just looking at them, what's trapped in them. Because if you think about, if you've ever been like to a puddle or a pond and what gets trapped in the ice, or if it freezes, gets broken up, refreezes again, that changes kind of the optical properties. So if you think about pictures that you've seen of icebergs, so like fjording in Alaska or in Antarctica, it's got that very distinctive blue, and it's not clear like an ice from the freezer would be. And it's because it's been compacted in this way. It doesn't have kind of a consistent texture. If you think about what I was saying about the fern, it was grainy and then it was packed. It's not cohesive sheet of ice. And so even though it's now solid ice, it fractures differently. It has a different look about it. There might be slightly different densities if you allowed me to pick up the different ice cubes. So I think offhand, you could definitely tell a distinct difference.
I feel like that would be a fun social activity at an ice conference. Name that ice
Party
cube.
games.
Guess the ice. Yeah. And who knows? We could bring it up a notch. Like, you're not a real glaciologist. You can tell me which
That's right.
glacier this is
Whoa.
from. Yeah.
Okay, play ice core or cocktail.
Absolutely.
And so I guess I commonly think of glaciers, I think of it in the context of them melting, rising sea levels, this kind of stuff. And so how does your research connect with that? I guess that's like a big concern.
Oh, sure. Yeah. So with my research in particular, because we're looking at mountain glaciers, they are very important to the ecosystem here currently and will continue to be so. They, on the global scale, are very small. We wouldn't typically think of them as having much of an impact on sea level rise. What we do think of is, like I said, they're kind of the headwaters to two big watersheds. So their seasonal melt really impacts downstream flows. So if you've ever been out here in the summertime and you're like, man, it's July or August and it's so hot and I should jump in this river or in this lake and it's freezing cold, is because it's just past the peak of the melt season. So the water is not warm because it's fresh off the glacier. So yeah, there's kind of a base flow to a lot of the rivers here, but we can see, and this is a lot of my work, is observed melt from the glacier, or in my case, my simulated melts, and then river flows. In the winter time, there's very little flow. It's whatever the base flow of your river is for that season. And then in the summer, it starts to heat up, and then midsummer is your peak melt, and then it fades away. So you get these seasonal spikes where you have quite a lot, and in some places in the province it's quite significant impact. They feed these rivers a lot. So you have this cyclical influx of glacier water, which is then necessary to downstream ecosystems. And this is a big, of course, agricultural province as well. So knowing a lot of the places are used to relying on these glacier fed streams. There's two questions when it comes to climate change, or there's a few related to my work specifically.
Sure.
So one question is, we talked about glacier retreat. These glaciers are small. Some of them are going to be gone soon because they're so small. So thinking about how much water do we use? How much water do we need? When will there be no more glacier water into these stream systems is a big question. So when is all the mass gone? Another question, though, is between now and then, how will this cyclicity change? Are these glaciers close to peak melt? Because there's going to be a summit of, as they, there's been noted, a couple studies recently have found that there's a feedback on a few of these glaciers related to forest fires. Some of the BC forest fires deposited debris on the surface of the glacier. You think of soot and stuff. So now they have a low albedo. So now they're melting faster.
Right.
So every summer when they melt a lot. So there's actually going to be an increase as these melt feedbacks play into each other, that they're going to reach a peak melt at some point where there's going to be a huge melt season. But after that, they're kind of past their prime mass and now they're on the decline. Like they're declining every year, but there's going to be a point where they can decline a lot because they have a lot of mass, and then you're past that point and now they're small. And so whatever, it's going to be kind of a slow melt, and whatever they feed the streams eventually is going to be a trickle. So knowing when that season is, or if that season's already past us and we're already on the decline where we can expect less and less every summer from the glaciers, that's another question from climate change as well. And then there's this is not necessarily my area, but all the ecological impacts, not only needing water, but it's been found that glacier-fed streams, because of their temperature, are very good natural carbon sequestration. So how much will they be able to do? Will they be able to continue to do that? And then again, when the glaciers are gone, what will our whole ecosystem look like as far as the impacts of carbon and other nutrients in the ecosystem? What's the river kind of ecology going to look like? And how's that going to affect everything here as well?
Wow.
That's amazing. And I guess in the Rockies, these are small glaciers on a global scale. What is the order of magnitude of lifespan that you would say they have left? Like decades, centuries?
Yeah.
Years?
For most of them, it's like, for instance, there was a study by Clark in 2015, kind of at the regional scale, all of Western Canada, looking at all of them. And because they are so small, most of them will be gone or lose the majority of their mass by the end of the century. Wow. So we just have a few decades left. So again, that timing of when are they going to be gone? Which ones are going to be left? So the Columbia ice field, a couple of other ones due to their topography will recede and be small, but then they'll hang out for a long time because they'll be shaded or whatever. But yeah, in the Canadian Rockies, it's a big area of study because a lot of people believe that they're on their way out, and quickly.
Yeah. Well, as you say, it sounds like it accelerates to a point, and then...
Yeah, it is in certain parts, certainly.
You got to go for that trip, Amanda.
I do.
You gotta
yeah, time's a ticking.
Yep.
You mentioned albedo earlier. Do you want to define that for our listeners who are unfamiliar with that term?
Yes. So albedo is the reflectivity of the surface. So not only does warm air and warm temperatures melt ice, but just even absorbing energy from the sun. So even on a cold day, if it's a sunny day and you have a low albedo, you can absorb energy and melt. And that can be even on a cloudy day. You don't need direct sunlight. So albedo is measured from high to low. So high albedo is high reflectivity, which means then you don't absorb a lot of energy. So think like a mirror or tin foil, you're bouncing back solar radiation, so you're not going to melt as much. Whereas low albedo is darker things that absorb a lot of stuff. So soot, like I mentioned, freshly tilled cropland. Think of walking in like a warm field or even grass on a sunny day. That's because it has a low albedo.
It's like why a black car heats up faster than a
white car. And your asphalt surfaces, all that sort of thing.
Yeah, and that's an issue with losing glaciers as well, right? That while they're there and they're mostly white or light colored, they're reflecting light and keeping us cooler than they will if they're gone. So it's part of that feedback loop of as it gets warmer, we lose the glaciers, and that speeds up the warming.
Man, I'm beginning to think this is bad.
That climate change is a problem?
That might be an issue.
Breaking news here on the Learn Real Good podcast.
That's
Oh.
right.
Amanda, I want to go back to your research actually. So how do you go about studying? You mentioned satellites, so you look at a lot of satellite imagery. What other ways do you go about sort of measuring the change in glaciers over time?
Oh, sure. So yeah, this is some of the nitty-gritty of glaciology as well, and kind of where our observational gaps are. So I'm a modeler. I use different models of glacier processes to try to simulate what they might do. Because as you can imagine, I've got 750 plus tiny glaciers out in the Rockies. No one's measured them all. No one's visited them all. I'm trying to figure out what they're going to do. So I have large scale observation data and I have small scale. So I have satellite imagery. I use digital elevation models, so kind of some topography of the surface of the glaciers from the Randolph Glacier Inventory, which is an international categorization of all glaciers on the surface of the earth. Gives me kind of their official boundary and their name or their number if they don't have a name, a poor nameless glacier. And then I use some micro scale data as well. So a few glaciers have been observed. So like Athabasca has been, Peyto, there's been a lot of work for several decades continuously at Hague Glacier. So people can actually go out and measure them. You know, they dig into, see where the Furin starts, what's that like. So yeah, I've got point scale for one individual glacier's small amount of data. And then I've got huge regional scale and I'm trying to fill in the gap in between. And that's a problem for a lot of glaciologists. So with my work, we're using mostly at the regional scale and then using some computer programs and stuff to interpolate in between. And then a lot of the physics is done by the model itself, trying to fill in. So we don't have, for instance, albedo measurements for this particular glacier. What's a good estimate? What can I calculate from this? How much solar radiation is it absorbing, you know, on this date in the past or in the future for this random little glacier.
And I guess my question next is, that was a weird intro.
You always introduce your questions by saying, I have a question.
I have
my question.
Was there something specific that attracted you to glaciers? Like you mentioned growing up in Montana. Did you like go visit a glacier and be like, that's it? That's what I want to hang out with all day.
I am fortunate enough to live close to Glacier National Park in Montana.
Nice.
So obviously I've seen them, love them, seen them change. But it's mostly kind of the sense of adventure. Like I said, I was really taken with tales of exploration. And I said, I love to ski. And so I was like, sign me up, ship me off to Antarctica. I don't even have to do science. Like, let me cook. I just want to see them up close and personal. Like, let's do it. They're gorgeous. Mountain glaciers are in their own way. So I think what I love about it, though, as a science and what really drives my research, like we've been talking about climate change and the importance of answering kind of what's next or what if. But I love that they are not only kind of a unique natural phenomenon that's gorgeous, but their impact and how tied they are to everything. Like I learn every day, you know, I've mentioned the ecology and their interesting physics and what's happening at the surface, in the middle, at the bottom, how glaciers are different glacier to glacier. I just love that they have every sort of science in them and that they're tied to everything else. So my work, I love kind of the fulfillment that I get, not only answering some of the big questions of what's the melt runoff going to be, when are they going to be gone, but also some more specific practical questions that can help other researchers or policymakers or people living here like know what's up with their glaciers. That's great.
You touched on the fact that glaciers and geology as a whole really has such an impact on everything else. And that's something I gained an appreciation for a couple years ago teaching a team taught course at McGill called The Evolving Earth. And so as a biologist, I was there to talk about like evolution of plants and animals, that whole story. But I taught alongside a geologist who talked about, you know, how the earth shape has changed and the topology has changed. And how it became so obvious from them talking how this is really underlying ecology, and the idea that I don't have any formal education in geology is just wild, because without understanding how tectonic plates move, right, that drives evolution. And these things are so tightly entwined. You can't really separate them, even though we try to force people into a tiny pigeonhole. All these sciences are really tied together and can learn so much from each other.
But also politically too. It's like as physical barriers of ice and snow retreat, then economic access to the Northwest Passage, mountain ranges, kind of affecting how political boundaries get set. Like all of these things are so tied together, and so glaciers, and it's something that it's not certainly in my day-to-day life, but it's so key. It's so fascinating how everything's interconnected.
Yes. Absolutely. It's beautiful. I love it.
So, Amanda, you've mentioned your goal. We know it. You want to go to Florida.
No.
Antarctica, right. So, have you been? Is that your plan?
Have you gotten close?
No, unfortunately. Especially with what's going on this last year. But yes, it's still on the horizon. It's less of a pipe dream than it was before. I still love looking. I know what research is happening there. I know what research teams are there. I know which universities do that sort of thing.
Nice.
So I would love to get involved in one of those projects. And even, like I said, not as a scientist either. If they need a cook, if they need someone to sweep the floors, reach out to me. I would love to be sent to experience it, to see it. It's gorgeous by day or by night, and by summer or winter too, like the aurora australis. I'd love to see down there. Just again, kind of all the different parts of life and science that is happening on such a unique continent. But in the meantime, still happy with my other glaciers.
Yeah.
Your little mini Antarcticas.
Yeah, for sure. And one of my dear mentors worked on the Greenland ice sheet, which is such a fascinating place of its own. The Alaskan Tidewater glaciers, very cool. The South American glaciers. Yeah, they're all over. They're still doing their thing.
And are you down to spend like a whole year in Antarctica?
Oh, yeah, man. Like people are like, oh, like you get, so in the States, you get a congressional medal if you spend a year in Antarctica, but it doesn't have to be a consecutive year. It could be 2 summers. And I'm like, that's such a cop out. Like you have to spend the winter.
Gotta be hardcore about
Come
it.
on, guys. No, yeah, I'm from a cold climate. Yeah, Florida, would be purgatory. Don't send me there. Send me myself.
So aside from just wanting to go to Antarctica, do you have plans on, do you want to continue in research? Do you want to do academia? Or are you just like, as long as I'm in Antarctica, I'm happy? Or do you have other specific goals?
I do have specific goals. It's kind of one thing at a time. So my PhD would be next. So whoever wants me to work on something for them, I'm down for that. My mom has a story. She doesn't know where I picked it up from. But I think she was cooking dinner one day or something, and I had been playing by myself. I was 3 or 4 years old, and I come over to her, and I say, Mom, I'm going to get my PhD. And I just walked off.
Wow.
She was like, what? Do you even know what you're saying? What where did you get that idea? So I've always had this idea in my head that I wanted to study something enough to then get a PhD. I just loved to learn. So yeah, I think right now academia is in my future. If they'll have me, I'm happy to be here. So yeah, PhD, whatever else after that. I love the theme of your guys' podcast because part of the appeal now to me of academia is not only the research, but the possibility of teaching as well, and inspiring and enabling other learners and young scientists would be awesome. So yeah, we'll see. But yeah, big bucket list, get PhD.
Sure.
Antarctica. And even if I have to go, like I'm resigned to the fact that if I just pay to go on the cruise myself, where you like go to Antarctica to see penguins or whatever, it's just going to be me and the old people. But you know what? I don't care. I'll be happy to be there.
I have a feeling you're just going to dress up as a penguin and sneak in, be like, don't notice me. Shh. Yeah.
Mission Impossible, Antarctica.
Amanda, you have been a fantastic guest. I have zero doubt you are getting to Antarctica, and I would love if you would email us and let us know.
Yeah, please send us a picture
We are pulling for you.
Thank you.
Pulling you on a glacier towards Antarctica.
Beautiful.
Thank you so much, Amanda, for joining us.
Yeah,
today.
thanks for having me.
Yeah, and you were so fantastic at explaining what is clearly a very complex
Yeah.
subject. So I think you'd be a fantastic educator as well.
Mhm.
So thank you
that
so
means a lot.
much.
Oh, appreciate it.
That was incredible.
Yeah, I had no idea all of this stuff was going on.
When I heard glaciers move,
Uh-huh.
like as a kid, I was like, no.
No,
Like, there's
like
no
you
way.
told them no, like glaciers stop.
Because when you see them, it's like, I don't even know. Maybe it was when I went to the Athabasca Glacier. The first time I went, I was 19. And like hearing that moves is just like, it's so huge.
Sure, it's like hearing that continents move.
But that's also true.
What?
Maybe that was your point.
Oh,
But
yes, it was.
yeah, it's nuts. And yeah, the effect they have. Like we were just talking the other day because we are in Montreal.
Yes,
And we get earthquakes from time to time, primarily driven from the fact that the island of Montreal is still rebounding from having been covered
by a glacier. Yeah, the weight of the glacier pushed it down so much.
Yes.
That without the glacier, it's coming back up, and we get earthquakes.
And for anyone familiar with Montreal, it's named for Mount Royal. There's a mountain.
Mm-hmm.
That's a generous term.
It's a hill.
There's a hill at the center of the island, and you can find like seashells embedded in it because it was underwater and under ice, and as that ice is moved, where the island is moving up, and that causes these itty bitty baby earthquakes. Glaciers, nuts.
Still relevant.
Yes. Still relevant after all these years.
Yeah. Who knew?
Who knew they'd have such staying power?
Well, Amanda knew, I guess. That's why we invited her.
I love that singular focus as a 3-year-old saying, I'm going to get a PhD. That would be spooky. Can you imagine like a little toddler saying that?
Yeah. Well, I don't know. It's spooky. Like, are they like in the mirror floating? That's spooky. If they like whisper, come into the bed at night, come into the room, I want to be a PhD. That's spooky.
That would be
It's
horrifying.
not precocious.
Yeah, precocious. Yeah, very. It's quite adorable.
Yeah,
and she's
very
doing
charming.
It.
And she's doing it.
Unlike me, I said I was going to be a neurosurgeon. There's a picture I drew where I wrote the word neurosurgeon very poorly in like senior kindergarten. Didn't make it.
But now you have a podcast. That's pretty close.
Hey, yeah, anyone can do brain surgery.
Yeah, but
not anyone can do a podcast.
All right, that's all right.
That's enough goofing off. Well, thank you, Vinny. Thank you, listeners. Thank you, Amanda, for being a fantastic guest.
Thank you, Katie.
Oh, yeah. And thank you, Science, for never ceasing. I feel like I'm accepting an Oscar.
Yeah, I'd like to thank Science.
It's so cool.
Yeah.
Right?
Very.
Are we in agreement?
We agree.
We conclude.
Learning very good.
Learning very good.
That's our sequel
that
podcast.
That should have been the name of this. Learning very good. All right. Vinny, why don't you send us off with our socials?
If you'd like to follow Learn Real Good, you can check us out on Facebook, Twitter, and Instagram at LRG Pod. That's Learn Real Good Podcast at LRG Pod.
That's it, folks.
That's us.
See you next week.